Okay, so we're starting with ionic naming, and those are specific types of chemical compounds. But we have to look at basically what a chemical compound means to begin with. So when it says it's a relative number of atoms in a chemical compound, do we know why that term relative is in there? Okay, it doesn't mean like necessarily if we're looking at a whole particle or a whole group of salt particles, there's not one sodium atom and one chlorine atom. Okay, there's one sodium atom for every chlorine atom that's in there. Okay, it's that 1-to-1 ratio that we see. So in water molecules, there is 2 hydrogen atoms for every oxygen atom, no matter what sample you look at. Okay, so that's what that chemical formula is telling us, is that for every oxygen atom, there should be 2 hydrogen atoms, no matter what sample you look at. It's that relative kind of ratio that we should see in a chemical formula. Does that make sense? Okay. Let's look at our periodic table. So you're going to need out your periodic table today, and I'm going to give you a new set of periodic table that will help you kind of look at these naming a little bit more. But let's look at a periodic table here. And let's review our valence electrons a little bit. Okay, first of all, somebody tell me what a valence electron is. What's a valence electron? Yes, Rachel.
An electron in its outer shell.
Perfect. Okay. And outermost electron available for bonding. So an outermost electron that is available for bonding. Okay. If we've got electrons in full lower shells, they're not available to bond, but our valence electrons are. Okay, and you'll see me, remember when I write that, what's that mean? An electron. Okay, and you'll even see me just write them like this, valence electrons, that's what that means. Okay, so you can abbreviate those things down so you're not taking so long. But you'll see me abbreviate with that electron. Okay, so let's review the number of valence electrons. How do we know how many valence electrons each atom or each element has? Do you remember the correlation to the periodic table? Oops. Okay, so to find our number of valence electrons, we have to look at the corresponding group number. And this is where it gets a little bit trickier with our group numbers. For group 1, that stays true. All of group 1 have 1 valence electron. 1 electron in their outer shell that's available to bond. Group 2 is the same thing. It has 2 valence electrons. The transition metals are a little bit more difficult to decipher. Okay, so we don't really have rules that we follow for the transition metals. When we get over to group 13, how many valence electrons do you think they have? Only 3, right? They can't have 13 outer electrons. They've got 3. So here we've got 4 valence electrons. Group 15 has 5. 16 has 6. 17 has 7. And how many does group 18 have? 8 valence electrons. So there's none in group 8 that are available to bond. Okay, group 8, that's the noble gases, right? They've got that full shell. So when we look at these chemical compounds and how they fit together, it has to do with the number of valence electrons they have and how apt they are to kind of take electrons from somebody or to donate them to someone else. Okay, so that's why we have to review that valence electrons. Okay. What does it mean for us to have an ion? We're doing kind of a whole review here before we get to naming. What's an ion mean? It has a charge. Good. And what is a positively charged atom called? A cation. And a negatively charged ion is called an anion. Okay, so now we're going to be able to look at these on the periodic table. Most of the time, where do the cations fall on the periodic table? The left side, the right side, the top, the bottom, the middle. Where do we think the cations are found? Anyone have an idea? The left side. Remember our stair step goes somewhere here? All these are our positively charged particles. All these are our negatively charged particles. Okay? You'll kind of see them. It actually goes a little bit less with the stair step than what I originally drew. Okay? You'll actually kind of see the split about group 4. Okay? So all these to the left of here are positively charged. To the right of that group 4 are negatively charged. So they don't quite follow the stair step like our metalloids do. But you'll see most of the cations, or all of the cations, lie on the left side of the periodic table. All of the anions fall on the right side of the periodic table. So when we look at these charges, do we see some patterns coming on? Group 1 all has a charge of +1. Group 2 all has a charge of +2. Okay, the transition metals get a little scary. Okay, but let's jump back over to group 13. This has 3 valence electrons, we said. What's the charge for group 13, most of them? +3. Okay, carbon and the group 4s, they get a little bit scary. So this is a little bit less of a pattern for us to follow. Then we start from the right side. So in group 8, how many valence electrons do they have to bond? None. So they can't have a charge. They're not going to bond with anybody. So this is a neutral charge. Okay? Group 7 or 17 has what charge? -1, -2, -3. Okay, so do we see how those kind of come in from either side of the periodic table? That's the patterns that we fall for charges. The reason these charges are the way they are is because basically if this group 1 would give up the 1 valence electron they have, which they give that electron up very easily, they would then have a +1 charge. Okay, if they give up that electron, they're 1 electron short of what they should be, so they have a +1 charge. Okay, same with group 2. If they give up their 2 valence electrons, which they're going to give those up really easily, if they give up their 2 valence electrons, then they're going to have a +2 charge. Does that make sense why those charges are the way they are? Okay. And then we go over to group 17. Fluorine has a -1 charge. What does fluorine want to do if it's got 7 valence electrons? It wants to take one. So it's taking in an extra one almost all the time. That's why it has that -1 charge. Does that make sense? Do we see the relationship as to why those charges count with those valence electrons? Okay, very good. Group 4 is tricky because they're half and half. So sometimes they give and sometimes they take. Okay? Okay, let's look at like chromium or manganese or iron. Yeah, they can have 2 charges. They can take on multiple charges. Okay, so those elements are very specific in that they can take on multiple charges. There's more elements than just listed here that could take on multiple charges, but these are the most common ones. Okay, so these really commonly can take on multiple charges. So we have them both listed there. Okay, ions. Okay, so we're going to name monatomic ions. What do you think monatomic means? Means single, right? Mono means 1. So we're going to deal with naming single ions first. Okay? And so naming a single ion means we would just try to name this atom, right? S-2. What is this element right here? Sulfur, but it's got a -2 charge, which means it's not just pure sulfur anymore. It's got a different name. Okay? And so the ending for anions, when they have a charge, they end in IDE. Let me erase that so it's a little nicer. IDE. Okay, so instead of sulfur, this S-2 is really called sulfide. Okay, and you see that's on your periodic table of ions. That's what it's called. It's already named that. They already did that for you. Okay, but that's really important is when we're dealing with these atoms that have come together into that bond, if it's an anion that bonded, we have to know that it's sulfide or phosphide or whatever. Okay, so let's look at Cl-. Okay, sometimes you'll see it as -1. I usually leave off the 1 if it's a charge. That is a 1. Okay, even if it's +1 or -1, I just usually give that symbol. Does that make sense? Okay, so if it's the symbol without the number, you just assume it's a 1. So if you see Cl-, what would be the name of that monatomic ion? Chloride. Okay, and if you saw something that looked just like this, Cl, what would that be called? Chlorine. Okay, so I need to make sure that you see the difference between those two things. Okay, charged and uncharged particles behave differently, and they have different names completely. So make sure that you understand if that has a charge, we have to be looking at that. Okay, and it's really important that you understand only anions end in IDE. Cations do not. Okay? So we good with monatomic anions? Okay, so let's look at how we name cations. Okay, cations are really easy to name. There's no change. There's no change. Okay, so Mg plus 2 is still just magnesium. Okay, so cations have no difference in their name between a charged and an uncharged particle. Okay, and do we see that's true on our periodic table of ions? Look at all your cations. Is there any change in their name? No. Okay. Okay, any questions about monatomic ions? Those are the easy ones. Now let's start putting some together here. Okay, today we're gonna start memorizing something called polyatomic ions. Okay, what does this word mean? Polyatomic. That'd be diatomic. More than one or many. Good. Poly means many. Very good. So polyatomic ions mean it's an ion made up of multiple atoms. It's not just a single atom. It's not just chloride or fluoride or whatever. Okay, polyatomic ions are ions with multiple atoms. And we're going to start memorizing these lists of polyatomic ions because polyatomic ions are pretty common. Okay, so in order to be able to be quick with your naming, you have to be able to memorize these polyatomic ions. So today at the end, I'll give you a list of some of these polyatomic ions that we're going to need to memorize. Okay, so I'll give you a list of that, but I just want you to kind of know what they are to begin with. Okay? Polyatomic means many. These are some examples of polyatomic ions that you will have to memorize. Okay? Oops. So this is an ion altogether, okay, and it's PO4 and it has a charge of -3. This is an ion, which is CO3. It has a charge of -2. So these are just things that you have to memorize, and you'll use them to bond with other atoms that would make a full compound, okay? The thing about polyatomic ions is that they have their own specific name, okay? They have their own name, and you'll just have to memorize the name that goes with that particular ion, okay? Okay, binary compounds. How many things do you think binary compounds are made up of? Two things. Very good. Okay, binary compounds are composed of only two elements. Okay, they're only composed of two elements. And the thing about binary compounds is that overall, the compound must have a neutral charge. Okay. Can anyone think of an example of a binary compound? There's lots that we use that are really common. What do you think? Carbon monoxide is a binary compound, but it's a covalent binary compound, and I'll explain the difference between those in a little bit. What do you put on your food to make it taste better? Salt. Okay, so let's think of this is a simple binary compound, NaCl. It's composed of two things, sodium and chlorine. Okay, what is the name of this compound right here? You know it. Sodium Is it chloride or chlorine? Yeah, why is it chloride? Yeah, because the chloride ion bonded with the sodium ion to form a neutral charge, right? This is overall a neutral atom, neutral compound. So sodium's charge before it bonded, what was it? +1. And what was chlorine or chloride's charge before it bonded? -1. Don't a positive and a minus make a neutral? Yeah. Okay? So you guys named this before you really even knew the rules, okay? So let's look at a couple other ones. Okay, questions here? We see that the cation does not change its name. The anion ends in IDE. Okay? It's important also, I don't know that I mentioned this, but when we do this ionic naming, it's always between a metal and a nonmetal. Okay? It's between a cation and an anion. And cations are metals. Okay? So a metal and a nonmetal. So all this naming that we're doing right now has to be between something on the left side and the right side of the periodic table. Okay? They have to come together. So let's look at another example. If I want to combine magnesium and bromide. Okay, so when we're trying to build these compounds, I know I want to make a compound out of magnesium and I want to make a compound out of bromide. So I'm just going to write them separately first. Okay, and I want to find out what the charges of these atoms are. What's the charge of magnesium? +2. And what's the charge of bromide? -1. Okay, and I'll go ahead and write that 1 there, even though, if I leave it out, do we understand that's a 1 still? Okay, so this is how we combine these. I'm going to show you 2 different ways. One of them is kind of a slick, kind of a shortcut way. One of them is very just kind of common sense. Okay, so you can do either way. You can do both. I don't care. Okay, the first way is kind of going to be our shortcut method. So what we're going to do is we're going to drop the signs, and we're going to cross these charges down to combine our compound to Mg1Br2. Okay, so let's check to see if this works to make it a neutral atom, right? If we have a 1 subscript, what can we do to that 1 subscript? We can drop it, right? We don't need a 1 subscript on that to tell us there's 1 magnesium. So if we know, oh my goodness, okay. So if we know that there is 1 magnesium atom, which has a charge of +2, and we know there are 2 bromine atoms that have a charge of -1, that gives us -2 and +2, which makes 0. Okay, so that's kind of our cross down method. We can cross those charges down. Okay, the other way that we can do this is simply by saying, and kind of thinking rationally here, if I have magnesium, which is +2, and bromine, which is -1, I need to know that I need to have 2 bromine atoms to cancel out that +2 charge. So I would just say this, MgBr2. Okay, both ways work. Both ways give us the same thing. The cross-down method will always work. This method will always work if you can just think about balancing the overall positives and negatives. Okay? So either way works okay. So tell me what the name of this molecule would be. Magnesium bromide. That's it. Magnesium bromide. Okay, simple enough, right? Okay, so our anions and our cations have to equal out. So we've got 2 bromides that each have a charge of -1, and 1 magnesium, which has a charge of +2. They give us a neutral atom. Let's try another combination between aluminum and oxygen. Okay, now I want you to see, I just want a combination of these 2 atoms somehow. Okay, I'm going to write them out by themselves first. Okay, and tell me what aluminum's charge is. +3. And oxygen or oxide, what's the charge of oxide? -2. Okay, so this is where it gets a little bit more complex to do our just balancing the charges method, right? Because it doesn't balance if we just say, 2 oxygen or whatever. We have to think about that a little bit bigger because we've got charges that can't just be multiplied into each other. Okay, so now we're going to cross down our charges, and we say Al2O3, right? I remove the signs, I cross my charges down, and I'm left with Al2O3. So now you need to check to make sure those charges cancel out. Aluminum has a +3 charge, and how many aluminum atoms do we have? 2, which gives us +6. Oxygen has a -2 charge, and there are 3 of them, which gives me a -6. Okay? +6 and -6 gives us an overall neutral charge. Okay, so the name of this molecule would be aluminum oxide. Okay? Very good. Let's say I had a compound named lithium nitride. We want to try to build that compound backwards. So the way we can start with this is we're going to start, we know lithium, and we know nitrogen is really just we know nitride is really just nitrogen with a charge, right? So nitride has a charge of -3. Lithium has a charge of +1. So I can do my cross-down method right from there. Okay, I'm going to get rid of my charges, which gives me Li3N. Do we agree?
Yes.
Good, very good. How's this feel? Simple enough so far? Okay, very good. Let's do a couple on your own and we'll check them. So let's see if I have... So you're going to give me either the symbol or you're going to give me the full name if I give you something else. Okay, we got 4 here. I want you to try on your own. Either give me the chemical formula or give me the name in words. CaI2. Raise your hand if you agree. Okay. Oh my. Ca. Potassium. Oops. Perfect. Okay, perfect. What about the third one? AlBr3. Preston, what do you think? Aluminum bromide. Good. And our last one. Stone, what do you think?
Ag2O.
Ag2O. Perfect. Silver has a +1 charge. Oxide has a -2, which is why we can have Ag2O. Very nice. Okay, feeling pretty good about ionic naming. Okay, a couple things to remember about ionic naming. Has to be between a cation and an anion. Okay, so a positive and a negative. Or in other words, it has to be between a metal and a non-metal. Okay, we will deal with naming multiple types of compounds, like covalent compounds, which are between 2 nonmetals. And we're going to name acids. Okay, and we're going to name bases. So there's lots of different things we have to remember. So there's certain rules for each. So make a note here that this rule for naming, these rules, they deal with ionic compounds only. Okay, so these are metals and nonmetals. Okay, a combination somewhere of the metal and a nonmetal. or a combination of a cation and an anion. Okay? Questions here? Okay, for the last little part of class today, I would like for you to start making flashcards for your polyatomic ions, because those are things that you need to memorize. So what I'm going to do is I'm going to go ahead and post the list up here of what you will need, of the ions you'll need to know. And then if you don't have flashcards, you can go get them from your locker, or I have some paper up here you can cut up into flashcards if you need to do that. Okay? So I'm going to post these words or these ions up here on the board.